The Large Hadron Collider has recorded more four-lepton events at high energy than the standard model predicts. And the excess has persisted across runs, datasets, and independent detector teams. The question is whether CERN is seeing statistical noise that will vanish with more data, detector background that was modeled incorrectly, or the first faint trace of a new particle that the standard model cannot account for. You are going to see why this tension exists, what makes it hard to resolve, and what the evidence eliminates from the usual explanations. Four-lepton events are the cleanest signature in particle physics because isolated electrons and muons are nearly impossible for detectors to mistake for noise. When the Higgs boson was discovered in 2012, physicists called the four-lepton decay channel the golden channel because it gave the sharpest mass peak with the least contamination. The detector records the energy and direction of each lepton, reconstructs the mass of the parent particle, and builds a spectrum. If a new heavy particle exists, it should appear as a narrow bump at a specific mass. If only known physics is happening, the spectrum should follow the smooth curve predicted by Monte Carlo simulations of standard model processes. The primary source of four-lepton events in the standard model is the production of two Z bosons, which then decay into lepton pairs. This ZZ background continuum is well understood in theory, but calculating it precisely at high energy requires knowing the momentum distribution of quarks inside the proton, the interference between different Feynman diagrams, and the contribution from gluon fusion processes that are notoriously difficult to compute. Small errors in any of these ingredients can tilt the predicted spectrum and create the appearance of a signal where none exists. Above 200 giga-electron volts in reconstructed mass, ATLAS and CMS have both recorded more four-lepton events than their simulations predict. The excess is not dramatic. It sits around 2 to 3 sigma in local significance, meaning that if you stare at one specific mass bin, the probability of seeing this many events by chance is roughly 1 in 100. But particle physics does not declare discovery at 3 sigma because of a statistical trap called the look elsewhere effect. When you scan thousands of mass bins across the entire spectrum, the odds that at least one bin will show a random 3 sigma fluctuation become nearly certain. A 3 sigma local blip often collapses to less than 1 sigma in global significance once you account for all the other places a bump could have appeared. This is why the field requires 5 sigma, roughly 1 in 3.5 million odds, before claiming a discovery. The four-lepton excess has not reached that threshold, but it has done something unusual. It has refused to go away. The data from run 1 at 8 tera-electron volts showed a small surplus. The data from run 2 at 13 tera-electron volts, with 5 times the collision count, showed it again. Independent analyses by ATLAS and CMS using different detector designs and calibration methods both see tension in the high-mass tail. This persistence across datasets is not proof of new physics, but it is enough to prevent physicists from dismissing it as a fluke. Physicists use the term structured background when data shows patterns that are too organized to be random noise, but not strong enough to claim a discovery. The phrase is diagnostic. It means the data does not fit the null hypothesis cleanly, but the deviation is not sharp enough to force a rewrite of theory. Structured background lives in a classification gap. It is not discovery, so it does not get a press release. It is not pure noise, so it does not get ignored. It gets filed as an open question and waits for more data. The problem is that classification itself becomes a form of gatekeeping. Labeling a signal as structured background parks it in a folder of curiosity. rather than a path to funding, follow-up experiments, or theoretical attention. If the excess is real, this delay costs years. If it is not real, chasing it wastes resources. The tension is sharpest in how the data breaks down by lepton flavor. The standard model mandates that electrons and muons are treated identically by all forces except gravity. This principle is called lepton universality. Any deviation from it would signal that a new force or particle couples to muons differently than it couples to electrons. When physicists separate four lepton events into channels like 4 muons, 2 electrons, and 2 muons, or 4 electrons, the excesses do not distribute evenly. Some channels show larger deviations than others, and the pattern does not match what you would expect from a simple miscalculation of the ZZ background. This flavor-dependent structure adds weight to the idea that the excess might not be a modeling error. One of the most powerful tools in the four-lepton channel is angular information. The leptons do not just carry energy, they fly apart at specific angles that encode the quantum numbers and charge parity properties of the parent particle. By measuring these angles, physicists can test whether the events came from a spin 0 particle, like the Higgs, a spin 1 particle, like a Z boson, or something else entirely. The angular distributions in the high mass excess are consistent with a heavy spin 1 particle, which is exactly what you would expect if a heavier cousin of the Z boson exists. Theoretical models call this hypothetical particle a Z prime. It would mediate a fifth fundamental force, couple preferentially to certain lepton flavors, and decay into lepton pairs just like the ordinary Z boson, but at a much higher mass. The Z prime is not a new idea. It appears in grand unified theories, extra-dimensional models, and extensions of the standard model that try to explain dark matter or the matter-antimatter asymmetry. What makes the four-lepton excess interesting is that it sits in the exact mass range and flavor structure that several Z prime models predict, but the data is not clean enough to confirm it. The bump is broad, the statistical significance is marginal, and alternative explanations have not been ruled out. One alternative is that the Monte Carlo simulation underestimates the ZZ background at high mass because of uncertainties in the parton distribution functions. These functions describe the probability of finding a quark or gluon carrying a certain fraction of the proton's momentum. At high momentum fractions, the functions become less constrained by data, and small errors can propagate into the predicted event rate. Another alternative is interference between the Higgs boson and the ZZ continuum. Even though the Higgs decays mostly at 125 giga-electron volts, its quantum field interferes with ZZ production at all masses, creating subtle dips and bumps in the spectrum. If this interference is modeled incorrectly, it can mimic a new particle. A third alternative is detector effects. Electrons lose energy as they pass through material in the detector, and the reconstruction algorithms must correct for this. If the correction is slightly wrong at high energy, it can shift events from one mass bin to another and create fake structure. Muons do not suffer from this problem as severely, which is why physicists expect a real signal to look sharper in 4 muon events than in 4 electron events. The data shows the opposite in some mass bins, which weakens the new physics interpretation. Physicists guard against fooling themselves by using blind analysis. They lock their event selection criteria, background models, and statistical methods before looking at the final data in the signal region. This prevents them from subconsciously tuning their models to fit the bumps they want to see. Both ATLAS and CMS follow this protocol, and both still see the excess, which means it is not an artifact of after-the-fact data massaging. But blind analysis does not protect against theory errors. If the standard model prediction for ZZ production is wrong by 10% at high mass, no amount of procedural rigor will catch it. The only way to test that is to improve the theoretical calculation or find an independent cross-check. One cross-check comes from B-meson decays. Over the past decade, experiments at the Large Hadron Collider, Beauty Experiment, and Bell have measured discrepancies in how B-mesons decay into electrons versus muons. The standard model predicts these rates should be identical up to tiny mass corrections, but the data shows a preference for muon decays that is inconsistent at the 3 to 4 sigma level. If a Z prime couples more strongly to muons than electrons, it would explain both the B-meson anomalies and the lepton flavor imbalance in the Four-Lepton excess. This connection is not proof, but it transforms the Four-Lepton data from an isolated oddity into part of a broader pattern. Another cross-check comes from the muon magnetic moment. The muon G-2 experiment at Fermilab has measured a deviation in how muons wobble in a magnetic field that disagrees with the standard model by 4.2 sigma. If a new force couples to muons, it would shift both the magnetic moment and the rate of muon production in high-energy collisions. The Four-Lepton excess at CERN and the muon anomaly at Fermilab could be two windows into the same hidden sector. The current run of the Large Hadron Collider, called Run 3, will provide enough data to settle the question. If the excess is real, it should grow in significance as more collisions are recorded. If it is a statistical fluctuation or a modeling error, it should wash out and disappear. The threshold for discovery is 5 sigma, which corresponds to a 1 in 3.5 million chance of a false positive. The Four-Lepton data is not there yet, but it is close enough that another few years of data could push it over the line, or kill it entirely. What the evidence eliminates is the idea that the Four-Lepton spectrum at high mass fits the standard model cleanly. The excess is faint, but it is persistent, flavor-dependent, and correlated with other lepton anomalies in B-mesons and muon spin. What the evidence does not yet eliminate is the possibility that improved calculations, better parton distribution functions, or refined detector corrections will make the excess vanish. The result still has no confirmed account. The strongest candidate is a Z-prime boson with preferential coupling to muons. But the statistical significance is not sufficient to claim discovery, and alternative explanations remain open. The mechanism or interpretation stays unresolved because the data sits in the gap between background and breakthrough, and only more collisions will force a verdict. What this changes is the understanding that particle physics is not just hunting for clean 5 sigma discoveries. It is also managing a portfolio of faint, structured signals that refuse to behave like pure noise and refuse to crystallize into certainty. The Four-Lepton excess is not a discovery, but it is not nothing. It is a pressure point where the standard model and the data do not quite agree, and pressure points are where the next layer of reality tends to crack open. If CERN is seeing the first trace of a new force, it will not announce itself with a bang. It will whisper through small deviations in lepton counts, flavor ratios, and angular distributions, until the whisper becomes undeniable. If you found this look at the edge of known physics valuable, consider subscribing for more breakdowns of where measurement meets mystery.